We now have this activity where they're mentioning a bar with a certain density function, 4 plus 0.1x. X equals 0 represents the left end of the bar. That will help us visualize it in a coordinate system. What we need to realize is we either need to use the point masses formula or the continuous mass distribution formula. So which one do you think we need to use? Take a quick moment to pause the video, think about it, and then restart. Okay, hopefully you had a chance to make a decision and you should have picked the continuous mass distribution. Okay, this integral formula is the one that we're going to need to use to solve the problems in this activity. Remember that the total mass of the bar was the denominator of this formula, because remember, density times length in the one-dimensional situation is what gives you mass. We have to integrate that from A to B. Now, how do we figure out what B is? We know A, the left end, is going to be x equals 0, but it says that the length is 20 centimeters, which means our B will be 20. And that's how we'll set up the integral to answer part A. For part B here, they're asking you, without doing any calculations, do you expect the center of mass to be equal to 10, less than 10, or greater than 10? Think about the behavior of this density function to help you answer that question. Then it says, for part C, compute x bar, which is the exact center of mass of the bar. In other words, you're going to use this formula exactly as is to do part C. The average density of the bar, for that, we need to recall the average value of a function, which is from, in this book, back in 4.3, when you first learn about the integral. So to find the average density of the bar, we're going to treat rho, our density function, as the function that we're taking the average value of. We have our A and our B, plug them into this formula, we're ready to move forward. Part E, we have a different density function that's called p of x, and it involves an exponential. We still have a bar whose length is 20 centimeters and whose left end is x equals 0. They're asking you to plot rho of x and p of x on the same axes, and then without doing any calculations, which bar do you expect to have the greater center of mass and why? To help you with this, you can type both of these functions into Desmos.com. Finally, they're going to ask you to compute the exact center of mass of the bar with that new density function. Compare it with E. Think about what observations you make at that point. All right, to sum up what we talked about in this section, when we have an object of density D with volume V and mass M, this is the most real-life scenario we can think of. We know that mass is density times volume. We talked about air being more dense than water because if I have a cube of air and a cube of the same size of water, the volume is going to be the same, but this cube will be heavier than the air cube. The water cube will be heavier than the air cube, and that's because water is more dense than air. Earlier in the section, we also talked about if you have a constant cross-sectional area for your object, such as a thin bar, and the density is distributed according to some density function rho of x. We can find the mass of the object by just doing integral from a to b of rho of x dx. For point masses, the center of mass is given by this formula, these sums, no integrals here. That's for point masses. If we have mass continuously distributed along an axis, in other words, we're imagining a thin bar as if it were a one-dimensional object with a density function rho of x. Again, constant cross-sectional area. We have this formula involving integrals for the center of mass. These types of integrals, a lot of times you'll have to do integration by parts for them. That's one of the reasons you learn integration by parts, is a lot of times you'll have x times some other function in your integrand, and the technique to solve that integral is to use integration by parts. So that's just a little tip for you as you proceed to try problems. And again, the notation we use for center of mass is called x bar, and center of mass is the balancing point of the system of masses, or of the portion of the bar you're considering.